All right, so we have been doing problems about proportions, and those were z-tests. We either had a 1 proportion z-test or a 2 proportion z-test. Now we are going to have problems about means, about averages. So these are now going to be quantities that we can do, and they will average together. Now, the problem with that, and so I'll kind of shortcut what all is it says here. The problem with a mean is that when they give you a mean, you need the mean of the population, which is this mu. In fact, let's write that out there. That is the mean of the population, okay, as opposed to x bar, which is the mean of your sample. Okay, so we'll need to keep those straight. Well, the situation is that we also, whenever we get data, we typically only have a sample. So, of course, this sigma is what? What do you know this sigma to be? Okay, so that is the standard deviation of the population. Okay, standard deviation of the population. We don't ever have that. I mean, rarely. In fact, I don't even know a case when we could have the standard deviation of the entire population. If I was estimating the average shoe size of everybody, I can't do that. I could take a sample and do that, but I cannot do the average shoe size for the whole population. So, because of that, we just have the standard deviation of a sample, and that's this little thing, S of x, and that is the, sorry, I should have had this written out somewhere else where you could write all this, standard deviation of a sample. Because we just have the standard deviation of a sample, we have a more varied curve than the perfect normal curve. So, in summary, we do not have the perfect normal curve anymore. We have something that is more varied because we only have the sample standard deviation. And these are called t-curves. So instead of being a z-curve, that was the perfect normal curve, we have a t-curve. So let's talk about what a t-curve looks like. They are still unimodal, they are still symmetric, and they are shaped just like the normal curve. But they have fatter tails, and they are more varied. T-curves are more varied than the perfect normal model. Okay, that's the key. The key is this right over here. The larger your sample size, the less varied it gets. Your standard deviation is getting smaller. So as n gets bigger, it's getting closer to the normal curve. If n is smaller, then it's more varied. So that's what you're wondering about, is how big is your sample size? Larger sample or a smaller sample? That'll tell you how varied it is. Okay, so let's put a little summary here. As your sample size goes to infinity, so as your sample size reaches the same size as your population, okay, your t-curve, so as then the t-curve approaches normal. So as your sample size gets bigger and bigger and bigger, your t-curve, which is varied, gets more perfectly normal. Okay? So you can see up here in these pictures, you see these different shaped curves? So those have to do with different size samples. There was this guy, and he came up with all of the probabilities for all of these different curves. And luckily, we don't have to do that. We don't even have to have a chart. Our calculator will calculate that for us, okay? It will find the t-curve and calculate for us. So here's a summary. The facts about t-distributions. They are bell-curved. They are still centered at a t-score of 0. The center of them is a t-score of 0. They are still symmetric about 0. There are a ton of different t-curves. there are a ton of different t-curves. They are all different from the perfect normal, and what tells us which t-curve to use? It's based off of sample size. Okay, so let's write a little note here. Sample size tells us which t-curve to use. Okay, and tell me again, what happens as your sample size gets bigger and bigger and bigger? What happens to the t-curve? It gets less varied and less varied, and it gets closer to the perfect normal model. Okay, good. So our sample size is going to tell us which t-curve to calculate off of, or at least it's going to let us tell our calculator which t-curve to calculate on. Okay, so let's move on down here, and let's talk about this thing called degrees of freedom. Okay, so our little video explained to you why we have the degrees of freedom as n minus 1, okay? So that's what we use it as every time we need it. All right, so that's it. That's all that is different from a one proportion z-test to a one mean t-test. So let's do a t-test. Here we go. We're going to run a t-test, and we're going to use a t-score instead of a z-score. All right, this is because we are doing t-curves and not the total normal curve. And so you know how z equals x minus the mean over the standard deviation? Remember that? So this is the sample mean. So t is the sample mean minus the population mean over the standard deviation of the sampling distribution. So I have this formula written down, and you'll always have this formula given to you, so you don't have to have it memorized, but that's how you'll fill in stuff. Now let's recall, what does the x bar stand for? What is mean of the sample? Good. Sample mean. Good. What does this mu stand for? Population mean. Okay. It's also typically our claimed average, our claimed average that they are wondering about. Okay? And then this is going to be our standard deviation information divided by the square root of, what's in? Sample size. Okay. Now, let's actually draw a t-curve down here. Oh, after we do that, we'll get our p-value, our probability, by doing t-CDF instead of norm CDF. Remember when we used to get a p-value, we would get it from norm CDF, but now we're going to get it from t-CDF, from the low t-score to the high t-score, but you have to tell the calculator which curve to compute off of, and so that's how you have DF there, degrees of freedom. You will have to tell the calculator the degrees of freedom. Okay, so one quick thing before we get going. Let's say that this is the perfect normal curve. Okay. I want to draw a t-curve. I want to draw one that has a sample size of 10. What can you tell me it's going to look like? How will it compare to this normal curve? A sample size of 10. It's going to be a lot flatter and wider and more varied. So let's say that we have this. This is a t-curve with n is 10. If n is 10, what's the degrees of freedom? 9. Good. The degrees of freedom is 9. Good. I'm going to draw one more, and I'm going to draw it in purple. I'm going to draw a t-curve. It's going to be a sample size of 50. How will a sample size of 50 look? Where will it be in comparison? It'll be closer to the normal curve, not as varied as this blue curve. Good. So will it be a perfect normal curve though? No. So it's going to be maybe a little bit more like this. So this one is still a t-curve. Yeah, the more flat one is 10, because it's so wide and so varied because it only has 10 in the sample. This one is a sample size of 50, and the degrees of freedom then would be 49. Very good. So it is getting closer to the normal curve. It's less varied than the blue curve, but it's not as good as the red curve. Okay, so let's move on and let's actually do a problem. So here we go. The tallest one was a normal curve. Yes, the smaller the sample size, the wider the curve. The smaller the sample size, the wider the curve. The normal curve's n size is infinity, like the whole population. So on the normal curve, n is the population, the whole population. Okay? All right, moving on. So Andre is a waiter in San Francisco. The Internal Revenue Service is doing an audit on his tax return this year. In particular, the IRS wants to know the average amount Andre gets for a tip. In an effort to satisfy the IRS, Andre took a random sample of 8 credit card receipts, each of which indicate his tip. The sample mean of 12.35 with a sample standard deviation of 2.25. Assume the distribution of tips is unimodal and symmetric. It's approximately normal, but so we know it's a T-curve because it's not completely normal. And that all the conditions have been met. Test the claim the IRS makes that Andre makes. They wonder if Andre makes more than $10 per tip on average. So, when we define our parameters, no proportions anymore. It's a mu. Mu is the average of, so that's always going to be your first word. Mu equals the average of all Andre's tips. So it's the population average of all of his tips. That's what we're going to make an inference about. We're going to take a sample of just 8 credit card receipts and infer about his entire average. So the null hypothesis is that what? He claimed what on his last tax return? He claimed that he made $10 on average per tip. He claimed that he made $10 per average, or on average, per tip. But the IRS suspects that he does what? Makes greater than $10 per tip on average. Okay, so we're going to come on down here and get some information. Compute the t-score and the p-value. So what is mu? What's the population mean that we are testing? $10. X bar, what is that? That is the sample mean. And so when he took his little sample, what was his sample mean? Yes, it says in the problem it is $12.35 and a sample standard deviation of 225. So this sample mean is 12, what did it say, 35? And this is the sample standard deviation. And that was 2.25. What's n? That's the number in the sample. And he took 8 credit card receipts. So that is your sample size. That means degrees of freedom is how much? 7. Okay, so I want you to set up what should go in this little t-score. I want you to fill in the blank of what goes in there. Go ahead and calculate that. And then it is kind of tricky on your calculator. I mean, we do need to make sure that we've got some correct calculator steps. So I need you to practice trying to get that. So I got my top part, And then I got the whole, then I did the bottom part. So I did those separately. Okay, to 2 decimal places. So I did the top and then I did the bottom. That's the best case for you because it's too difficult to do those all in one calculator steps on your calculator, okay? And so that is a t-score of 2.94. Oh, is it 2.95? What? Okay, so let's see here. Because this is an issue if we can't get everything to come out correctly. All right, so I know the top is 235. Let's do 2.25 divided by the square root of 8. And I got 0.80. That's what that rounds to. It's 0.80. So 2.35 divided by 0.80 is 2.94. Okay? All right. Now, let's calculate the p-value. So see, what this is saying is you have a t-curve, which is more varied, and you are out here at 2.94. You got a sample right here at 2.94. Where's the p-value? Which direction do I shade? What would be we want to see if it's higher than $10. So therefore, this is the p-value that I'm interested in finding. So we're going to do this. We're going to TCDF. What is the low t-score? This is a t-score of 2.94. 2.94. What is my high t-score? That's infinity. So what am I putting for infinity? 99, comma 99. Comma degrees of freedom, which is 7. Okay, so now we're going to go to our calculator. All right, and so here's where you find that on your calculator. You go second vars. Number 6 is TCDF. Number 6 on mine. Oh, it's 5 on yours? Okay, so on mine it's 6 TCDF. And then I'm going to go from it. You might have the menu that shows lower bound is 2.94. Upper bound is 99. And then degrees of freedom, 7. So if you have the menu, then you put your numbers in that way. If not, you put it separated by commas. You hit enter and it's 0.011. 0.011. You know we go to 2 significant digits, 0.011. All right, so there's that. So we're going to then compare our p-value to alpha. Oh, did I miss a box? Oh, yeah. Okay, that's my, it's 0.011 and I move it 2 decimals, so 1.1. I mean, I don't know, just leave it as a decimal, 0.011. I guess just whatever your p-value is, put that there, okay? The probability of getting that is 0.011. All right, so that's your p-value. So my p-value, which is 0.011, how do I compare that to alpha? It is less than. So if it is less than, what am I going to do? So I reject HO because a p-value is low. So the HO has to go. And if I reject HO, then what do I say about the alternative? Good. So there is evidence that the average of all Andre's tips is greater than $10. So what's the IRS going to do? Fine him. Yeah, they're going to make him have to pay more money. Okay? All right, so I'm just going to do that one, and I'm about to skip to a problem that's a little bit different so that you can do this tomorrow. Let's go to skip example 2. It's the same thing. And go to example 3, but the values on example 3 are wrong. So I want you to go type these into your calculator. So the values on number 3 are wrong. I want you to use these instead. And then I want you to calculate the one variable stats for that. Okay, so let me give you a few moments to type that in and get those numbers. All right, so I might have confused you a little bit, but you went to stat edit and you put these stat edit and you put all these into list 1, and there's 15 numbers there. Okay? Okay. And so once we have those in there, we need to get some information. So let's actually go ahead and read this problem down here and fill in what it's talking about. Okay? So a Las Vegas casino advertises its slot machines in a certain area of the casino has an average of 95% payback. So they say that when you put your money in, you will make on average 95% of your money back. A simple random sample of 15 slot machines were tested to see if the average payback was different than 95%. And so this data was on the other page here. We want to see if it really is lower. We suspect that the casino actually pays back less money than 95% payback. Okay, so fix that on the problem. We want to see if it pays back less than 95%. Okay, so what would be the parameter? Mu stands for, and what's the first word we put? Good. So what is this? The average what? Good. It's the average payback percent of these slot machines. Of all these slot machines. Okay? The average payback percentage of all these slot machines. That's why all the numbers you put in were decimals, because they represented percentage paybacks. Okay, but we're going to average all of those. Okay, so we'll move on to the next one, and we entered in all of this data. And so, what's our null hypothesis? That the average payback percent is 0.95. The casino claims 95% payback. But we think they're ripping us off. And we think it's less than 0.95. Okay? All right. So the average number, let's fill in our things here. Mu is what? Okay, 0.95. Good. Now, look at these other things. I do know N. What's the sample size N? 15. Good. And DF is 14. Good. Okay, now, you actually could get this X bar and this S of X by computing the one variable stats in your calculator. So that's what we're going to do, is get this average and the standard deviation of that data. So, here in your calculator, you have your stuff in list 1. Let's go find the average and the standard deviation of that, okay? So, stat over to calc. And you see the first one there is one variable stats. So to do that, stats, okay, so let's write these steps down so you can remember them tomorrow. So stats over to calc, and that's where you find one variable stats. Okay, so I'm going to do one variable stats, hit enter, and you want to do those of list 1. It defaults to that, list 1, and you hit enter until you get your numbers, and looky there. There's my information I want, okay? So of this printout, here is my X bar. That's the sample mean. So I'm going to put down 2 decimal places, 0.92, And then what is the standard deviation? It's this one that's the little s of x. So it's the 0.024. Two significant digits, 0.024. So those are the numbers that you use. X bar and s of x. Okay? So now, let's go write these things out. I want you to fill in this t-score formula. Do that now. Okay, so if you did that t-score correctly, well, 0.0062. Go to two significant digits. So this should have 0.0062 on the bottom because you want to go to two significant digits. All right. So now let's get the p-value. So my p-value is going to be TCDF. Now I'm going lower than. We think that it is ripping us off and that we're going lower than this. Yes. So we think that we are going down here to negative 99. So it's negative 99 up to negative 4.84, comma 14 degrees of freedom. And so let's figure that out here. So TCDF is number 6 on my calculator, negative 99 to negative 4.84, and then 14 degrees of freedom. Oh, look at there. 1.31 times 10 to the negative 4. So what do you have to say about that? It's about 0. So this is less than 0.9. I know. I think it's this x bar down here, 0.92. The probability that you got this sample or something more extreme is pretty much 0%. Okay, no. I think we always... Oh yeah, we did put 10. We sure did. You know what? I'm not sure. So I guess I sure did put 10. Okay, so then let's do that. 0.95. Okay. No worries. 0.95. Okay, we'll leave it right there. I'll think about that and get back to you. Okay, compare your p-value to alpha. What do you have to say about that? Yeah, our p-value of about 0 is less than alpha. So what are we going to do? We're going to reject HO. So therefore, we have evidence that, and then what would we say? The average payback percent is less than 95%. So we got evidence that they're screwing us over and that they actually pay back less than 95%, and they say they pay back 95%. Okay, so your assignment is going to be that next section on this practice, okay? And so